Okay, so now we are working on question 3, which is one from module 3, chemistry of the elements, right? And so we see figure 1 here is showing us the melting points of the elements in period 3. And so we can see the melting points here on the y-axis and the element is here on the x-axis, right? And so the first question is saying that part A, explain in terms of structure and bonding why aluminum has a higher melting point than sodium, right? So why would aluminum, as is shown here, have a higher melting point than sodium, which is way down here at around 495, and aluminum is at around, what would that be, say 980, right? So why is that so? Well, let's start by talking about the structure and bonding that's present in both these metals that we're comparing, right? So let's start by writing that out here, right? So both of these both metals have a giant metallic structure, but as we move from sodium to aluminum, we have to think about what's changing, right? So as we move from sodium to aluminum, let's extend this a little bit more. As we move from sodium to aluminum, right, what we see is that the number of electrons that get donated to the sea of delocalized electrons increase, right? Because now we have more electrons. So we have more electrons to contribute to that sea of delocalized electrons, right? Which are then bonded to positive ions, right? Because remember, that's what we have going on in metallic bonding, right? So what we're saying so far is that both of them have a giant metallic structure, but as we move from sodium to aluminum, the number of electrons that get donated to the sea of delocalized electrons increase, right? And so the combination then of the increased delocalized electrons, so let's write that, the combination of the increased delocalized electrons and the ionic charge of Al, right? And that ionic charge is going to be a +3, right? It forms a +3 ion. The net effect of that results is that we have greater electrostatic attraction between ions. So that would be your positive ions, right? And the electrons. This results in stronger that are then harder to overcome to melt the aluminum. All right, so that should suffice for that. So both metals, they have a giant metallic structure. So first we start out by talking about what structure and bonding they have, right? They both have a metallic structure. And we know that in metallic bonding, we have delocalized electrons, as in a sea of delocalized electrons, and there are positive ions surrounding that, right? So as we move from sodium to aluminum, the number of electrons that get donated to that sea of delocalized electrons increase because we have more electrons in aluminum. The combination of the increased delocalized electrons and the ionic charge of Al, which is a +3, whereas sodium is a +1, results in greater electrostatic attractions between the positive ions and the electrons. And as a result, right, as a result of that, then you know that we're gonna have to overcome some greater forces to move from one state to another. And in this particular case, we're melting. So to move from that solid state to a liquid state, we're gonna need to exert more energy. And that's why you see that the melting point is higher for aluminum when compared to sodium. Okay, so let's clear this and move along. So the other one is asking us to explain why silicon has the highest melting point in the period. So in the entire period, period 3, silicon has the highest melting point. Why is that? And so we have to explain that for 2 marks. So let's get to it then. What it comes down to, right, is that silicon forms a giant covalent lattice that is like diamond, right? So you know that diamond is like a very comprehensive network. Silicon forms something like that, right? So silicon forms a giant covalent lattice that is like diamond, right? This requires a lot of energy because we have to break a large number of strong covalent bonds because it's a network now, right? It's a network of bonds. So we have to break large number of strong covalent bonds. Right? So that's a huge distinction here, and we could say that, and that should suffice as to why it has the highest melting point, right? So it forms a giant covalent lattice that is like diamond, and it requires a lot of energy because we have to break the large number of strong metallic bonds, and this results in it having the highest melting point in the period, okay? So then moving along, sulfur melts at a higher temperature than sulfur. So let's just look at that. Sulfur is up here and phosphorus is down here. So sulfur melts at a higher temperature than phosphorus, just slightly higher. And they're asking us to explain that phenomenon using structure and bonding. So what we can say here, let's start by talking about the structure that's present in both of them, right? Structure and bonding in both of them. So both the sulfur and the phosphorus have simple molecular structure, right? Simple molecular structure. But the difference is that S, right, sulfur melts higher because it has greater van der Waals forces of attraction and also I think most importantly here is that it has more points of contact between neighboring molecules. And by that, what do we mean? If we look at how we find sulfur in nature, right? Generally what we have is we have a S8, right? So that's 8 sulfur atoms, right? So that's many more points of contact when we compare that to phosphorus, which is generally seen as P4, right? So because of that, there are many more points of contact in sulfur between neighboring molecules than there are in phosphorus. And so in addition to that, the greater van der Waals forces in sulfur, because sulfur has a higher number of electrons, then we will see that it has a higher temperature than phosphorus, okay? So all of this should suffice for the 3 marks. Make sure you hit on this points of contact point though as well, right? So more points of contact between neighboring molecules, and that should be good for 3 marks. So let's clear this and keep it moving right along. So this part now, part B, is focused on the reactions of oxides of magnesium and phosphorus with water, right? So we're looking at how the oxides of these period 3 elements react with water. So in the first row, we have the oxide, magnesium oxide, and then we have P4O10. And so the first question is saying complete table 2 by describing, right? So just describe the reaction of each oxide with water and suggest a pH value for the resulting liquid. So we just have to describe what would happen, not so much write an equation at that point, right? So we're just gonna describe the reaction of each oxide with water, and then we're gonna suggest a pH value, right, for the resulting liquid. So the reaction with water and MgO, right, is that it's gonna react to form, so let me write that up here, reacts to form insoluble hydroxide, right? An insoluble hydroxide is what we're gonna get there, right? And of course, if we get an insoluble hydroxide or any hydroxide for that matter, that means that we're gonna have a pH of around 8, right? So not a super strong hydroxide there, but just a little bit slightly above neutral. So we'll have a pH of 8 for that resulting liquid. And then when we look at P4O10, what's gonna happen is it's gonna react with water. So we're just describing the reaction at this point, right? So reacts with water to form acidic solution. So you can kind of see the distinction here, right? One forms an insoluble hydroxide, the MgO, one forms acidic solution. So of course, the resulting pH is going to be different, right? For both of those resulting liquids. And so in this case, for the P4O10, we get a pH of 2, right? So just keep that in mind there, is that you might have different acid-base character of the resulting compound that forms when the MgO result with water, reacts with water, versus the P4O10 reacts with water, right? And so in this first case, we're going to get a pH of 8. That's more on the basic side of things. And then we're going to have a 2 resulting from the P4O10 when that reacts with water. So it's on the more of the acidic side of things, right? So that's 2 marks. That should suffice. So let's clear this and move down. So write the equation which represents the reaction of water with P4O10. All right. So this P4O10 is a solid oxide. So let's write that. Make sure we have our state symbols as well. So this would be P4O10 solid, right? And it's gonna just be reacting with water, right? And then now, when it does that, we're actually gonna get a very strong acid, right? Which is called phosphoric acid. So that's our result there. That's how we can produce phosphoric acid from that, right? So this is gonna be an aqueous acid. And let's just make sure that we're all balanced. We need to put a 6 before this hydrogen. Let's see. So put a 6 before this hydrogen, we need to put a 4 here. And now we're all completely balanced, right? So that's pretty much how the reaction would go. when P4O10 reacts with water, right? We're gonna get phosphoric acid, and that's what gave us a characteristic pH of 2 that we saw up top, but it's a fairly strong acid, right? So that's that. And let's see how many marks that was. That was 2 marks. Okay, so we're good for our 2 marks there. We've balanced it, we've written our state symbols, and we've shown our correct products. So we're good for our 2 marks there, okay? All right, so let's clear that, and we're gonna be moving down to part C. And part C is asking us to write equation to show what happens when each of the following chlorides, so now we're looking at the chlorides of period 3 elements, and how these chlorides then react with water, right? So in the previous one, we were looking at oxides and their reaction with water. Now we're looking at chlorides and their reaction with water. So they're asking us to write an equation for silicon tetrachloride reacting with water. So let's just do that one first. So that one will be, will go like this. So we will have our SiCl4, right? And that exists as a liquid. And when that reacts with water, right, what we're gonna get as a result of that is silicon dioxide. So we're gonna get SiO2 solid. And then also we're gonna get 4HCl as well, right? So we're gonna get some HCl gas coming off there as well. And let's just make sure that we're nice and balanced. So to make sure that we're balanced, we're gonna add a 2 here in front of this hydrogen, right? All right, so then that's for silicon tetrachloride. That's what we would get. Those are our products, and we're balanced, so we're good for our 2 marks. Now let's move on to aluminum chloride, right? For aluminum chloride, what's gonna happen is we're gonna have our AlCl3, and that exists as a solid, naturally, right? And so then we're gonna have water going with that to give us, we're going to get a hydroxide in this case, so we're going to get aluminum hydroxide. So that's a more basic solution there, right? But we also have these acid fumes that come off as well, just as in the case above. So we get these acid fumes here. So make sure that you're aware of that, right? Because that might be something that you could look out for in terms of observations to tell you what's going on there, right? So just to recap, silicon tetrachloride with water forms silicon dioxide and HCl. Aluminum chloride with water is going to form aluminum hydroxide and also hydrogen chloride gas, okay? All right, so that is where we wrap up question 3. Yes, so that's the end of question 3 there. So we are ready to move on to question 4. So let's just clear this.